Hello and welcome to another Würth Elektronik webinar. My name is Silas Zorn and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar. The topic of today is impact of elevated voltage and temperature on molded power inductors in DC-DC converters. Our speaker today is Efren Bernal. Efren.
Thank you for having me.
Cool to have you here. Thank you. And he will hold the presentation, and after that he will answer your questions. One information from my side: you will be muted during this webinar. This means that you cannot ask us questions via your microphone, but you have the opportunity to ask your questions via the chat function. And after the presentation from Efren, we make a short Q&A session, and then Efren will answer your questions. So after the webinar today, you will all receive the link to the recording from today and the presentation. And now I wish you an exciting webinar, and I give over to you, Efren.
Thank you so much, and welcome everybody here. We are going to speak about some important findings for Würth Elektronik. I'm product manager. I work with Molded Power Inductors, and I take part of the research groups that get us to these amazing findings. And just a short agenda led us to say that we are going to say why Molded Power Inductors are so important for us in the current market, and what is about this degradation. There is a phenomenon behind, and we are going to speak about percolation as well, how we get that. So it's a long-term research, two different kind of research topics, and we found a similar phenomenon, that is percolation. Then we are going to see how we can find the percolation, how is able to recognize that problem, and how affect you in a normal DC-DC converter design. Let us to start with the market trends. So molded power inductor is a market that is still growing up. Even in the current days that we have strong problems with the economy and so on, the projection for molded power inductor is that we are going to go for, until 2.5 millions that from now, and more closer to 5 million. And that is with a CAGR of 6.6%. And that is a huge potential for molded power inductors. But why? And what is that trend? So the dynamics go in direction of the new technologies, like for example GaN technologies, the new families of SiC, but as well the influence of automotive. But the increase of the efficiency and the high demand for reliability of molded power inductors is an open question for us. So there is a strong trend into the market, but the open question is going to be how will we perform this kind of molded power inductors when we want to jump, for example, for designs like this silicon-based 2 kilowatts until the one by using GaN technologies, same amount of power but shorter 2.8 times. So then comes the question, so if we are speaking about artificial intelligence, we are speaking about embedded system, dedicated system, we are speaking about wireless 6.0 and this kind of technologies, the customer wants us to offer solutions that can run in smaller cases. What about the temperature? What is about the increase of the temperature into the inductor? And what about the voltage? Because we know that this kind of technologies is silicon technologies that go a higher voltage, then we get the opportunity to jump from buses of 480 volts and go directly to 5 volts and so on. So this kind of application allow us to say it's something that we need to take care. So reliability is something that we concerned. And why? Because the question is, as you know, a DC converter, in this case a bus converter, so we have a huge amount of voltage input and we want to decrease the voltage at the output. Normally we have the losses already fixed, or we actually said that the inductor has not a big role into the losses and the reliability in terms of time. Why? Once you fix the design, we expect that the losses, as in this picture we can see, are no higher than 15%. Could be a little higher, could be a little lower, for sure depends on which kind of inductor are you using and the design itself. But the question is, if we imagine a scenario with a constant voltage input and constant voltage output with a constant demand of energy, then we expect that the current through the inductor or the ripple current is going to be almost fixed, the same. But when we speak about reliability, we expect that the first one to fail is going to be the capacitors. Then let us speak about the cooling system. That is the ones that's going to fail. There is a lot of things that can fail, but we never thought that one of the failure reasons could be the inductors. And there is concern based on molded power inductors because, you know, the technology is totally new for some of the customers. When we speak about why we expect that the ripple current should be constant, we need to go a little behind the definition on an inductor. We already know that an inductor is fixed. You have the same permeability, you have the same area, the same number of turns, the same distance. So from the physical point of view and the geometry, we can say that the inductance should not change. Okay, for sure, if the permeability changes, the inductor is going to change. Like there are topics like the saturation current, how can affect you. But if we move a little on, this ripple current that we're speaking about, the variation of the ripple current can be fixed if we have the same switching frequency, we have the same input voltage, output voltage. So if we plan very well our design, we doesn't expect a variation on the ripple current. That is important to speak here because more of the constant value in terms of reliability are the inductors. So people who work in that direction comes to us asking, okay, why I have expect a failure? And that is the point of today. So let us to see this video. So in this video, you can see the ripple current with green color. We can see the voltage through the inductor with a blue color, and we can see the harmonics. And there is a failure at one point. So we can see that the ripple current increase, and in the B part of the figure, we can see that the demand of the power increase as well. At one point that I should turn off the power source. So that is the phenomenon that we discover. A phenomenon that affects molded inductors when they are running into a design in a real application. The name, percolation. And that is totally new for the industry. There is some research topics about it. But in this case, the question is, why is changing? How is related that with the inductor himself? So maybe the temperature, maybe we work into higher temperature. Let us to see this figure. We have two power inductors for families in Würth Elektronik's portfolio. We have the blue one that correspond to a molded power inductor with something called soft saturation. And the orange ones correspond to a power inductor with hard saturation. So we have a gap here between 40 amperes, 60 amperes, and those are the curves of a temperature around 20 degrees. But if we increase the temperature, we expect a strong change for the case of the hard saturation in power inductor. So now you can see if you plan it that the inductor works between 40 and 60 amperes, then the inductance value is going to decrease dramatically. So that's the strong advantage of molded power inductors. On the other hand, we can see here that the problem before from the oscilloscope video was not related with the increase of the temperature because we expect that the inductance value are going to keep almost the same for the range that we are looking for. But that is the theory. So the theory is that should be no change. But the reality is that there is a behavior that could change drastically the performance or your design. But why is not really a problem of saturation? That was one of the questions from the customer that really know about this topic. Let's see here this simulation. So that is the ripple current going through the curve of BH. So if you keep between the linear part of the curve, you doesn't expect a change into the ripple current. If you have a hard saturation material and you go over the limit, so let us to see that at that point there is a change of the ripple but in the peak. But it's not this transition that we saw before. So we are not speaking about it's really influence of the change of the permeability itself in this case. Here we can see a little more detailed explanation about it. So for an inductor of 10 microhenries, if we want that they were around 1 ampere, this is going to be the limit because the behavior looks like a soft-saturation material. So if you keep between that part, that is the linear part of the BH curve, then you are like in the safely area. If you overload the inductor, then you are going to suffer. But let us to keep with the difference between the green color ripple current and the peak that we are seeing due to saturation. So at the end, we want to emphasize that this is not really a problem regarding the molded inductor, the interaction of the particles, and they get saturated or something like that. What is then the reason behind? For that, I would like to introduce you a little about how is the construction of the molded power inductors. Here we can see in the figure 6, example one of the new generation of our molded power inductors, and it's almost like a copper wire. We press that with some iron powder, so literally a powder. So we put it, we glue it, and then we put into the oven. And internally, we are speaking about different kind of particles. Those particles are glued, but not before applying a coating to get a coating layer. So just imagine that now we're speaking about, iron particles, then we can have a strong amount of eddy current losses, but in this case, this coating layer allows us to control the eddy current losses. So we don't expect losses after you do the measures, you run an application at red expert, and you know the amount of power loss that you expect for your design. But in this case, that is the thing that is changed over the time. And they change in the way of a percolation network. So here we can see an illustration about the percolation. So we can imagine that the particles before were these ones. So could be connected or not, but the particles are in a safely area until fell. It's something like there is an open space here, and it starts something like an electrical connection, thermal or electrical connection. So then the particles are going to be connected, and that means a flow, an internal flow of energy at that point. And that is the percolation phenomenon. And it's related with a material degradation. And that allows us to say that the material was like in an insulated state, and now we are moving like to a conductive state. That is the electrical representation. If we see it, percolation is something that is related with materials, and we have like a insulation zone where everything performed as expected, but at one point, once we have to have in those small short circuits, then start the percolation networks, and at one point are so much that they jump until the conductive zone. And that is the phenomenon itself, and can be used for civil engineering, for another kind of plastic material, whatever kind of things that deals with metals, with conductive materials. So how we get that? And that is very important because we were working two research teams, once with the definition of what is the maximum voltage that a molded power inductors can achieve. And another one was, okay, what is the maximal temperature? There is people speaking about thermal aging of molded power inductors. We found that we suffer of the same of the same phenomenon due to the same results at the end with the change of the ripple current, and a little more about the change of the performance of the inductors and the Q curve, for example. But percolation is not a new phenomenon. So we already know that exists percolation, and we already know about degradation, but we released already an application note to summarize these findings. Before, we have an application note related with the voltage specifications, and we have another one regarding thermal aging on molded power inductors. But here is the summary of this percolation. We can do it by putting a resistor in parallel to the inductor. So let us to say that higher electrical and thermal stress on molded power inductors can lead to an increase of the magnetic core losses or eddy core losses. There is still the open question, okay, are really eddy current losses or are a new kind of losses? At the end, it's an increase of the core loss. And that's deal with the with the flow of an energy through the material. Why is that not part of, for example, of qualification of the components? So in our application note regarding voltage specifications, we use the example of the same article, once before another one after application of a high voltage exposition. And you can see here, according with the regulation of the SAQ and the instruction set, we have any kind of problem. You can see that the inductance came between the parameters and the resistance as well. But in the reality, we saw that there is this change of the ripple current. So like a step here. And that step is represented by a resistance. So let us to say that we can see here that we keep with the same ripple behavior, but we add a resistant component that represents these core losses. For sure, it's not linear, so we are working on that to get a better model for this percolation. It's a total new phenomenon, but that is the representation. So at this point, just let us to imagine what is going to happen with our design if we add a resistor in parallel to our power inductor. That is the open question for you. Why? Because normally we say that this resistor is so high. So we are speaking about thousands, hundreds of thousands of ohms. But in this case, it's going to decrease around some milliohms. And that is just like a short circuit. That is the effect. On the other hand, we have the results of the thermal aging application of research team. We can see here traditional metal alloy soft magnetic materials, the ones that if you expose it to higher temperature, they get immediately through cracks. But the new generation of materials, we have no experience with cracks, and we can assume that if you do the measure of the resistance and the inductance and you have no cracks, that maybe we doesn't suffer about percolation, or in this case was thermal aging. But in the reality, if we move a little more, we are going to find that in this case, and competitor grade 1, that means that 125 degrees, but even they promise that can go higher. When you expose to higher temperatures, almost all the coating is burned. So you can see that it's burning parts, just like here. But even though if you use a competitor part, grade 0, that means that higher temperatures that run a lot of the tests as the ASAQ recommends, you can find a small spots here when you can see that the beginning of the phenomenon. In our case, after these research years, we can offer some kind of combination of glue, coating, and the different kind of particles to get no evidence of this percolation or thermal aging. But if we focus a little more in this, so the first percolated or customers formations can be showed like these networks, percolated networks. And that was the one that we say, okay, how we can model it should be something behind. Then we move with some materials research people to introduce the topic, what's going on, and we get the name. So, but about these limits of temperature, you can find it in our thermal aging application note. But what was the change of the ripple current? One of the steps goes, okay, what is the effect if we do the measure before and after high voltage or high temperature of the Q value versus frequency? You can see here that the yellow one means that you have a high Q value, close to 100 at this medium range of frequencies, and you can see that a strong decrease here to the higher frequencies label, actually closer to the resonance frequency. The same can happen to impedance. So in the impedance, you can see here the problem of the resistance, but as well here. That is the important part. Why we were not able to find it for ACQ results? Because normally competitors and we, like 20, 30 years ago, we only do the measure around 100 kilohertz. And at 100 kilohertz, you cannot see changes of the Q value, in this case the L value as well, and the resistance in series, because that is the one that we measure, like the resistance of the wire, and the wire has no change, has no role with the percolation. That is why we cannot see the effect of percolation. In our case was because we normally do this kind of Q values curves before and after ICQ. That is how we found it, and you can find those results in the previous application notes. But let us say that a decrease on the Q value means a strong increase on the losses. Here are a summary for you at this point of what is then percolation affectation. When we speak about that the initial step of percolation are not visible easily, even for us. So the Q value doesn't change so much. But once you move in deep into the percolation area, you are going to see the change of the Q value, maybe not changes of the operational range of frequency, switching frequency, because in this case, for this inductor was 10 microhenries, a size of 4 millimeters. So we're speaking about no higher of 350 or something like that kilohertz. But if you move a higher frequencies, you can find it. Over the time, if you're exposed to more temperature or you're exposed to high voltage, then you're going to see the effect of the conductive area. And remember, why we cannot see just a resistor, just a line? Because we still have the wire. The wire is there. So we still have an inductor, but with a different permeability. On the other hand, interesting was that when we use the same competitor part and we compared due to high voltage and high temperature, we found that the curves change for both the scenarios. So we have one part exposed to 120 volts. We apply a round of shots to 120 volts. We put it in a real applications, and due to our voltage specification, we guarantee that the part was performing well. But I increased the voltage a little with some peaks of 190 volts. And then with some peaks, the curve changed, as we can see here in the light blue color. On the other hand, I use the part at normal temperature range, and I increase the temperature range until around 200 degrees. And we saw as well the beginning of percolation. The curves, the change of the shapes of the behavior is not the same. Why? For sure, the particles that are affected at the beginning are those closer to the terminals in the case of the voltage, high voltage exposition, and the external particles in the case of temperature. But at the end, we start with one network, another network, and with the time, almost all the material are affected. So we doesn't keep it until 1,000 hours of test as the ACQ recommend. We go further. So you can see in my application also that we only show results until 1,000. Now we go until 5,000 hours to see how our parts performs and how parts competitors perform. You can see, for example, here this was a competitor that we say, okay, it's very close to us, but at one point they go down dramatically. So at this point we say that the decrease of the quality factor is almost 400% to zero. So another competitor, just with some time exposition of higher temperature, they fell. Or parts show some changes as well. But we can see that for this scenario, that is a size 1040, you need to reach around 40% of decrease of the Q value to increase twice the core losses. So maybe it's something that we can handle, but we are total transparent with you that the phenomenon can appear if you expose the components to higher temperature. Then comes the question from some customer, okay, but that means that for me it's nothing to do because I only operate my parts around 40, 60 degrees plus cell heating, no more than 100 degrees. Then we repeat the test at different temperatures. We set the same point criteria, 40% of decrease of the Q value represent 100% of decrease of the losses. For us, that is a failure because your design going to change dramatically. So we do the test and you can see that there is a strong correlation with an error of almost 0.99. And based on that, if you use the part at 85 degrees, you expect that the part is going to fail, to have a failure around 10,000 hours, almost 1 year and a half. Though this kind of curves, Arrhenius plot curves, allow us to show you that if you choose a wrong part, you are not safe if you work it at lower temperatures. You can have the effect. So it's not that if you offer a part that can work until 150 degrees, that you are safe if you work in this area. No. Can be as well that you doesn't suffer of that if you offer a solution that runs 1 hour per day, 3-4 days per week. So yeah, for sure, that is a Arrhenius plot. In this case, is a product work or component working 24 hours of the day, 7 hours, 7 days of the week. So it's a continuous working. But in industrial components, we really need that. We offer solutions with 10, 20 years of guarantee that works, runs all the time. Just the Wi-Fi modem that we have at home, we never shut down that. It's always running. So we wanted then to show you a real affectation based on boards that we have for you. So we even include a filter at the input. It's not maybe necessary, but some customers say us, yeah, maybe there is influence, external influence, so we want to avoid that. We have a fixed load here, around 6.5 watts, with a fixed current, 2 amperes, 5 output voltage or output, and we use a boot converter, DC-DC converter to run the test. Here are the same video before, the same demand of power and how it's related with the part of the cure or percolation. We can see that if you are working in the safe area, then you are going to work from insulation area and with the time to percolation area. So then let us run the same simulation by doing click into the video. Then we have here how that increase, and then we are going to have how increase the power demand. So you can see that at one point the power demand is going to jump faster and we have a failure here on our component. So coming back, so when we have the phenomenon, we are going to see that the part move from one area to the other one. And that is why we move so fast, because at one point we are going to have that the part percolated is going to be faster burned. That is the summary of this. Let's go one step at the other one. Maybe the video is a little confusing for you. So at the beginning, in this case, I did the measures with some oscilloscope coupling, but we have a little jitter here, and it's important for me. So we have some jitters here. So in the voltage, you can see it as well in the ripple current. The ripple current is perfect. We are not speaking about hard saturation. We are speaking about 40% of ripple current, and the harmonics here, okay, maybe are related with the connection points. Once this percolation starts, then you can see that even here the harmonics doesn't change so much. If we move a little further, then we are going to see how we can see an increase of the harmonics. But wait, the jitter here decreased. So we don't, as you can see, comparing this point, almost we have nothing of jitter. So the one that are increasing is the step. And we have a huge amount of harmonics. And that is something that we concern about it. Yes. Why we have this huge amount of harmonics? For sure. Our model before represent a resistance. So it's a step, and a step in terms of series of Fourier means an infinite amount of harmonics. So if we translate to the video before about the demand, the power demand, we can see that the increase of the power source demand goes from 50% in this case on almost 80%, 30% more. But for sure, if we take a reference 85% of efficiency in this case, we can have a decrease until almost 55%. So 50% of decrease if you use as reference 85 of our efficiency. And for most of application, the battery is out. So we are going to have this kind of problem. Maybe, I don't know, it's a bad example, but just imagine the cell phone that after that 1 year failed. The battery is not working anymore. Was something related? Maybe with the molded inductor that is inside of the DC converter into the cell phone? That is a good one question that we get. But at the end, it's the same result for you. How far we are going to move from this part to this part, for sure depends on the application, depends of which kind of technology of molded power inductor are using, how often is running the application itself, but the effect is the same for everybody. So you can plan everything, the best inductor, the best transistor, the best controller, feedback, current feedback, voltage feedback, everything. You can fix everything. You can take care about a good one cooling system that doesn't fail with the time, proper maintenance. Let us speak about solar converter, for example, of PCs that you need to clean it with over the time. You do everything, all the maintenance. But even though you are going to see a decrease in the efficiency, on the other hand, a strong increase of the power demand. And that is not speaking about just energy itself, but if we go back to the increase of the harmonics, okay, is this an increase of the MEC? So we are going to speak about radiated or conducted MEC, because for sure that amount of energy is going to be present into the inductor, and for sure the temperature is going to increase. At one point, so high, yes, but what happens if the harmonics are not burned? What happens if the harmonics are radiated or passed through the final application to the load? What if you have an embedded system? What if we have a Wi-Fi 6.0 equipment that are very susceptible to this kind of harmonics? Just imagine a noise in the power source, and you have the filter, everything, but did you consider into your filter this kind of harmonics? Most of us, we don't do that. So, as summary at this point, then I'm going to say that we launched an application note to summarize these effects on molded power inductors degradation due to exposition to high temperature or high voltage. And high temperature, remember, is you accelerate the effect. But if you work at some high temperature like 85 degrees, you can suffer a percolation. If you work at high voltage, okay, some peaks of voltage can start it. Once one coating layer is broken, once you start jumping electrons between the material, percolation phenomenon is for sure a material degradation and involves everything. Which kind of material are you using? The size of the material. What was the pressure that you used to create the components? We're speaking about new technologies on molded inductors like co-sinter, transfer technology, hot molding, but even though everything is related, because at the end we have a coating layer, we have some glue in between, we are using organic combination with non-organics, and to guarantee for sure the soft saturation, but on the other hand, we can suffer percolation. You can find some evidence of percolation if you compare the Q values at higher frequencies. If you use a normal RCR meter and you do the measure of the L value at higher frequencies, maybe you can see some changes, but the stronger one in this case is going to be the Q value. And for sure, the ripple current itself. The question for me is, okay, if you have already an application running, how can you see the ripple current? Or how can you see the Q value? Because that's also one part of the problems. You have a reclamation from a customer, you start to looking for the problem, you take out the capacitor, and everything okay, you take out the inductor. If you take out the inductor and only do the typical measure of L and R, you are going to find that the guilty guy should be another one. Then you jump to the design team, maybe the controller, maybe the load, and at the end was this phenomenon. So we offer for you some solution in that direction. We have our standard industrial parts and we have automotive parts. And both of them are, you can find with the HT name, that are the high temperature, because at this point, when we launched the material was thinking about thermal aging. So this percolation is the result after the research that we have in Würth Elektronik. So if you have an application and you're really concerned, okay, I'm going to have some peaks, for example, I saw a customer, I'm going to go a little higher in terms of saturation, 40%, 50 milliseconds, double time, the performance rated current, but that happened almost one time every hour. Then we can speak about I'm having this kind of application when the connection point, they have some jumps onto voltage and whatever. So then we strongly recommend you to use high temperature version of the current LHMI or MAPI from us. We tested more than 5,000 hours, 200 degrees without decrease of the electrical performance to tell you we don't suffer percolation so that you need to concern about it. So thank you so much for your attention. We are open for questions, but if you need some extra support, please contact directly your sales guys, contact guy. If you have extra questions, you can write to me or to Annika Fremule, that is my colleague that we work together in this kind of topics.
So, yeah, thank you, Efren, for your interesting presentation. Now we will come to your questions. Before we start with the Q&A, I will share the handout from today. Now you can download it on the right side. Okay, then we can start with the first question. Does inductor core temperature increase once percolation starts? Will it run away?
That is an interesting question, really. So we speak about that it's not a phenomenon that you can avoid. So once the percolation starts, once you have a network, that network is going to have a strong behavior in terms of temperature, and the neighborhood parts are going to be affected as well. So yeah, at one point, that was the problem with our client. So we test the part, we said, okay, we use our components, maybe capacitor were the faulty, we change the capacitors, and after 1 year, once more the problems with the customer. And that is why we start working about maybe the temperature, and we try to find it, and was a runaway. So at the first months of testing, nothing happened. But once I started the percolation, no one can stop it.
Okay, thank you. Then, next question. I think the next question is a question about the page in your handout. Let me see this one. Yeah, the question was, this seems similar to dielectric failure of insulators. Can you prevent this by increasing the dielectric strength of insulating coating?
That is as well a good one question. So thank you for my colleagues behind. Now we can see here how we add this kind of coating. So if you increase the coating layer, then the question is going to be, okay, and what happened with the permeability? So when we have this kind of behavior, we are looking that all the magnetic field go through all the particles here in order to save energy and release that energy soft. But if you have a stronger one, then you change the air gap, then you decrease the performance of saturation. And more important in this case is, for example, some competitors, they see the problem by allowing the use of no organic coating materials, but then they offer you a range for one size of 3-4 inductance values, because you cannot play around with the benefits of molded inductors and materials to offer smaller or bigger inductance value, because the size is too smaller. So you really need this kind of advantages of the concept itself of molded. But yeah, increasing it is not a solution in itself. It's really what is the epoxy that you use for that coating. So, and it's not just the coating. I would like to emphasize as well the binder. So we can see that the binder disappears at one point with the microscope pictures. We found traces that we lost that kind of binder, and then the problem is going to be that for some competitor the part just going to go back to pulp, to pulver. So that is another problem as well.
Okay, thank you. And then I think it's one last question left in the chat. This one. How can I detect inductor with percolation as an engineer? Which material suffers against it?
That is an important question. So we have different kind of generations of material for molded power inductors. So for sure, those ones, carbonyl materials can suffer more, but on the other hand, every kind of alation in which you have a binder will suffer about it. Yeah, there is a new trend that the parts can deal with can be coated with into an oven around 80 degrees. But in this case, the limit is the wire. So you cannot use current wire. You need to use almost like a clip. So you cannot find inductors higher than 200 nanohenries or 300 nanohenries. So for bit 1 inductance value, let us say bit 1 between 1 100 microhenries, it's not possible to use that kind of technologies. We are working on that. Promise, in coming years we are going to see a new technology to solve that. But in this case, really we need to see your application, and in order to recommend you the better solution for you. So we can keep in contact about it.
Okay, perfect. Cool. Then we are finished with the webinar today. When you have questions, you can write into the chat, and then Efren will answer it via email in the next days. So now, thank you for joining. Thank you for your attention. Have a nice day, and hopefully we see us on our next webinar. Thank you and goodbye.
Goodbye.